So the first project I want to show you is 203, which is really very nice. There's an extra credit I did because of Kirk, in fact. So this is a missing step in my projects until now. This is password-based key derivation. This is what really happens, for example, on an iPhone or many other devices where you put in a password to get at your stuff. And this is what happens, for example, at password managers like LastPass. LastPass got hacked a couple weeks ago. An intruder got on their servers and stole the data, but they said it's okay because we don't have your passwords. You can only get a password. You can only get your passwords with your master password, and we don't have that. And this is how that works. And it works on any system you can install Python and such on, including my Mac here. So let me just get a terminal window. All right. So I've already installed PyCryptodome on this machine, so I can just run it in Python 3. Let me show you this. So I run Python 3, and then we can import HashLib, which we've used before, and then you can find out what's in HashLib with help of HashLib. This is the online system to see what's inside a Python library. And so you see it tells you what it does, and so on. You can go down page by page. And if you go down to the bottom, you'll see what we need near the bottom here. And there it is, PBKDF2 HMAC. This is a password-based key derivation function 2. This is a very common one. It's very similar to the process you use to hash passwords, to save them. So you choose a hash, you add a password, and you can add a salt. It's optional. And then you have a number of iterations and a desired key length. So it will take the password and it will run it through the hash with the salt, and then it will hash the hash and hash the hash and hash the hash again for this many iterations, and then it will just take this many bits out of it to give you a key of that means. So you can take a password and turn it into a key of any length by just choosing those other parameters. So, for example, here is how you calculate a hash of the word apple and get a 16-bit key, a 16-byte key, pardon me, there. So this is going to use MD5 on Apple, 1 round with no salt, and give me a 16-byte key, and there's the 16 bytes. All right. One thing actually that puzzles me is that MD5 is only 128 bits. Oh, that is 16 bytes, isn't it? Okay, MD5 is long enough to do this. I was thinking MD5 is not long enough to give you 16 bytes, but I think it is 68, 40, it's just long enough. So I guess if you tried to get a 32-byte key, it would fail. Let's see. It does. Okay, I don't know how it does that. Maybe it repeats. AA7? Nope, it doesn't just repeat. Okay, anyway, that's interesting, and I don't quite know how it does that. Probably the HMAC is part. It's a little bit more complicated than just using an MD5. It's using a methods authentication code, which we'll talk about later. So I guess you can get even more. All right. What's that?
The first 16 is identical.
Yeah, the first 16 is identical, but somehow there's more. Yeah, so the HMAC can get you more. I think we'll find out in later chapters a little more about how this works, but I don't know off the top of my head how I can get longer. Anyway, so now you got some challenges. You can use this SHA-1 with a different salts with 1,000 iterations and a different password and get a hash function and get a 4-byte hash. You can get really short hashes. Like if I want just 4 bytes, I can do that, and there you go. It looks like it's just trimming something first. So, all right, and so now there's some challenges here. This one here has a password as a 3-digit number, and all the rest is the same as the last one. So you can do it with Python and other languages. If you do it in Python, you have to do a lot of conversions from number to string and from string to bytes. So I have a link here that shows examples of how to do that. And here's the way this is actually used in a lot of popular systems like encrypting hard drives, which is what Kirk pointed out to me. So this is the user enters a password which is used to derive a key, which then encrypts data with AES. And I think this is how your passcode works on your phone and everything else. And it's how it works in LastPass. Your master password is used to get a key which decrypts the data, and they never have it. All they handle is encrypted data. They deliver it to you from the cloud on your device, but without your master password, they can't get at it, and neither can anybody else. This is the best way to do it. Your secret is not shared with anybody. So this one here, this is how the two work together. So let me run this, and then I'll talk about it. All right. So now I import HashLib and AES. Now I just get a 16-byte key from a password of Apple using MD5 and no salt. Now I create a cipher object. I have some clear text, which is this thing: any nation that does not honor its heroes will not long endure. It's a quote from Abraham Lincoln. And so then this is the encrypted ciphertext. That's how you do it, which is much more sensible. You know, in all our mathematical talks, we talk about how you start from a key, but where did you get the key? And in many cases, you just get it from a password, and this is how. The user has a password, you turn it into a key this way, and then you encrypt and decrypt with it. So you can decrypt it with this here. You have to make a new AES object. I was surprised you had to repeat this line. Cipher is new, AES new. You have to make a new AES object in order to decrypt. You can't do encrypt and then decrypt with the same object, which is rude. But there you go. This will take that ciphertext, and again, there's an issue of converting it. You have to make bytes from hex, and then you can just decrypt it and get back to your plain text again. So that's encrypting and decrypting with a password derived from a key, and now you've got some challenges. Here's some, and here you can have got a 3 lowercase letters, so you have relatively small key spaces so you can hunt through them and find them. And then encrypted virtual machines, which is where it all started. This is how VMware encrypts the hard drives on virtual machines. That was the question that originally came from one of my students, so I could look into it. And here's how it works. This is a VMX file of a virtual machine I encrypted. And you just use VMware, and you can go into the settings and choose to have an encrypted virtual machine, and it will add this. This is called the key safe. And this, I think, is how all the keychains work, like Apple's keychain and stuff. Well, I'm not sure exactly about that. But they create this thing called a key safe, VMware key list pairs. There's various objects in here. So if you just substitute the special characters like %2f and %2d with the real characters and put in some carriage returns, this information looks like this. So this is the key safe. Notice there's some kind of base 64 up there, but that doesn't matter. These are the only 3 things that matter. Pass to key. Here's the algorithm, AES 256, 10,000 rounds, HMAC SHA-1. Here's the salt, and here's the data. So this is called a key safe. You can hide a key in here, and it's safe. It's protected by the password the user has to apply. So the first one is an unimportant ID number. I spelled that better and placed it. There we are. Anyway, the second one is the salt, here. And the third one is the encrypted data. So you can totally reverse it with this Python. You take this data and put it here. Then you take, this is the salt. The key is here, and you have to know the password, of course. So to know the password, in my case, I used 123123, and you know it. So if you know the password, you can deduce the key. The key is 32 bytes because this is AES 256, and you can decrypt it. And when you do it, it turns into this key, AES 256. It is a key. So the key safe contains another key, and this is how it's done. They encrypt all the data on the hard drive with a randomly generated key, and then they encrypt the key with your password. So that way you can change your password or something. That's the way it's simple. That's the way it's usually done, 2 stages. So your password is needed to break in here, and then you just get a key that will access all the data on the drive. And that's the trick. And so here's another one. This is a safe you have to crack into. This is with 10,000 rounds. And it was, I think 10,000 rounds is normal for encrypting hard drives. And I think, yeah, I did this one. This is a harder safe. I guess I didn't put it in. One of these was, this is what LastPass uses for the encryption on your hard drive. And I think I just used VMware here, but I did do it on LastPass, which is even more. It's like 100,000 rounds or something. Anyway, so that's a useful thing to see how password-based key derivation is used with AES. So let me stop this one.